Hello there, my amazing people, students, lovers of chemistry, and all subscribers to my YouTube channel out there. I am super excited to be here with you on today's video on this series of gas laws that we've been treating thus far. We've looked at the Boyle's law, we've looked at the Charles law, and today we want to look at yet another equally interesting concept that is called the Gay-Lussac's law. And it's the law that talks about the relationship that occurs between pressure and temperature when the volume is kept constant. Now, let's talk a bit about what the Gay-Lussac's law represents, and let's see if we can treat some examples under it to buttress our points. So first of all, the Gay-Lussac's law is a law that shows the relationship that occurs between pressure and temperature of a gas when the volume stays constant. So when we're talking about the relationship that occurs between pressure P and temperature T of a gas while you keep the volume constant, that is where Gay-Lussac's law comes into play. What does the law state? The law states that the pressure exerted by a gas of a given mass at a constant volume is directly proportional to its absolute temperature. So if I were to write this law using mathematical terms, I would say pressure P is directly proportional to its absolute temperature. P is directly proportional to T. So what do we do over here? We can make this sign of proportionality to become an equality sign. How do we do that? We simply introduce a constant K. So it becomes P is equal to KT. So if we make this K the subject of the formula, it simply becomes P over T is equal to K. So that means whenever you're dealing with the Gay-Lussac's law, the product of dividing P by T will always be constant. So that means P1 over T1 will be equal to P2 over T2, which will be equal to P3 over T3, and so on and so forth. That is the Gay-Lussac's law for you. Now, the key idea behind this law is that when you heat a gas in a sealed container, that sealed container has the same volume. The pressure increases. Now, this is why they tell you that you should not keep your gas cylinders that contains your cooking gas or LPG. You should not keep them in environments that are hot, because the heat will make the pressure inside those sealed containers to become so intense that they can explode. So that's the Gay-Lussac's law in play over there. And when you cool a gas in a sealed container, the pressure reduces. Now, this is a very direct relationship, because as temperature increases, pressure increases as well. And if temperature goes down, pressure will also go down as well. Now that we've talked about all of that, let's move on to the next concept that we want to make clear. Are there examples to buttress our points? Yes, there are a whole lot of examples, and here are some of them. Example number one is the aerosol can that you have. Now, the cans that contains your perfumes, the cans that contains some of these things that you use in your house on a daily basis are called aerosol cans. And heating them too much, cans like your perfume cans, your insecticide cans, and the rest of them, heating them too much increases the pressure inside of them, and too much heat can make them explode. That is why when you check the instructions at the back of these aerosol cans, it is explicitly stated that you do not discard them by burning them in fire. It can cause an explosion. Why? Because as temperature increases, so does the pressure inside of them. So now that brings us to the next example, and this where most of us are familiar with it. It's the example of pressure cookers. Now, why are they called pressure cookers? It's simple and straightforward, because they use pressure to make food get done faster. How does it work? Pressure cookers are electrical appliances that are used in the kitchen that use high heat, which increases the pressure inside of them, and that makes your food to cook faster. This is what many people use to make beans to get done faster, because usually beans doesn't take a little while to get done. It takes an extended period of time. So with the aid of the pressure cooker that uses increased temperature, which also leads to increased pressure. It makes our food to get done easier and faster. So now the third example that we want to talk about under the Gay-Lussac's law is the example of your car tires on a hot day. Have you ever parked your car in the sun, and then after a while you see that I've even seen scenarios where a car was parked in the sun and after a while the tire just exploded. Why? That tire is a sealed container. There is no space for the air to escape. So heating up the environment where that car tire is will simply make the pressure inside of it to get intense and more. So heated air expands and pressure goes up inside the car tire, making the tire to feel firmer and stronger. It's the same thing that happens to your footballs that are placed um in a hot environment. They feel firmer. So that brings us to the formula for the Gay-Lussac's law. The formula states that P1 divided by T1 is equal to P2 over T2. You saw how we derived it. The law states that the pressure of a gas is directly proportional to its temperature. So when we introduced a constant to change this proportionality sign to an equality sign, it became P is equal to KT. And to make this K the subject of the formula, we simply said P over T is equal to K. What this means is the answer from dividing pressure by temperature will always be a constant. So P1 over T1 will be equal to P2 over T2, will be equal to P3 over T3, and so on and so forth. So now here are the names of all the variables involved in this calculation. P1 stands for the initial pressure, or the pressure that you started with. T1 stands for the initial temperature, or the temperature that you started with. P2 stands for the final pressure, or the pressure that you end with, while T2 on the other hand stands for the final temperature, or the temperature that you end with. Now it is also important to note, I've stated this before, but it bears repeating again, that you always have to convert your temperatures to Kelvin. If it is the concept of gas laws you're dealing with, it is important to make sure that your temperatures are converted into Kelvin so that your answers can be accurate. So now that we've said that, let's see if we can deal with some questions to apply the concept of the Gay-Lussac's law, and let's see where that will lead us. So we have the first example over here. Example number 1 states that we have a sealed gas, and it says a gas in a sealed can has a pressure of 1.2 atmospheres at 27 degrees Celsius. What will the pressure be if the temperature rises to 87 degrees Celsius? Volume remains constant. So let's get our variables aligned out. First things first, a gas in a sealed can has a pressure of 1.2 atmospheres. So we have P1 being equal to 1.2 atm. The next thing they said is that it has a temperature of 27 degrees Celsius. So T1, which is initial temperature, is equal to 27 degrees Celsius. 27 degrees Celsius needs to be converted to Kelvin. And to do that, we simply add 273. When we add 273 to 27, that gives us 300 Kelvin. So we have P1, we have T1. The question now says, what will the pressure be? Which means we're looking for P2, or the final pressure, if the temperature rises to 87 degrees Celsius. So T2 is equal to 87 degrees Celsius. So let's convert this to Kelvin by adding 273. When we say 87 plus 273, that gives us a figure of 360 Kelvin. So we have P1, we have T1, we have T2. Let's go ahead and find P2. So the formula says P1 over T1 is equal to P2 over T2. Let's impute our variables. P1 is 1.2 divided by T1, which is 300. This is equal to P2, which is unknown, divided by T2, which is 360. At this point, we can cross multiply, and doing that gives us 360 multiplied by 1.2 is equal to 300 multiplied by P2. So now that we've done that, 360 multiplied by 1.2 gives us 432. So this becomes 432 and this becomes 300 P2. So to find P2, we simply divide both sides by 300. 300 cancels 300. So therefore, P2 will now be equal to 432 divided by 300. That gives us 1.44 atmospheres or 1.44 atm. So you can see now the gas in the sealed container started with 27 degrees Celsius and the temperature increased to 87 degrees Celsius. So temperature increased and so did the pressure. The pressure increased as well because the initial pressure was 1.2 atmospheres, but the final pressure was 1.4 atmospheres. So you can see that temperature in this case was actually directly proportional to the pressure because pressure increased as temperature also increased. Now that we've solved that question, let's see if we can deal with yet another example and then we'll proceed to check out some practice questions for you. Example number 2 says a rigid tank. Rigid simply means the volume doesn't change. It is sealed. That rigid tank holds a gas at 5.0 atmospheres. So the initial pressure P1 is 5.0 atm and a temperature of 300 Kelvin. So T1 is 300 Kelvin. Now, since they've given the temperature to us in Kelvin, means we do not need to undergo any conversion whatsoever because it's given to us in Kelvin. The question now says, what is the pressure? So P2 is what we're looking for in this case. It's unknown. If the tank cools to 250 degrees Kelvin. So T2 is 250 Kelvin. So now let's impute our variables into the formula that says P1 over T1 is equal to P2 over T2. What's P1 in this case? P1 is 5.0 divided by T1, which is 300. That is equal to P2, which is unknown, divided by T2, which is 250. So let's cross multiply. Doing that gives us 5 times 250 being equal to 300 multiplied by P2. So 5 multiplied by 250 gives us 1250. And then this becomes 300 P2. So to find P2, we simply divide both sides by 300. So over here, 300 cancels 300. P2 now becomes 1250 divided by 300. So that becomes 4.167. What's the unit? Atmospheres, because pressure in this case was measured in atmospheres. Now check this out. The temperature reduced because we started with 300 Kelvin, but we ended with 250 Kelvin. Since the temperature reduced, let's check if the pressure also reduced. We started with 5.0 atmospheres. Now see, we are ending with 4.167 atmospheres. So the pressure also reduced. So you can see that the Gay-Lussac's law actually comes into play in this question because as the temperature reduced, the pressure reduced as well. So the two variables are actually directly proportional to each other. So here are some practice questions that I want you to try out your hands on. I'll be waiting for your answers right there in the comment section. So do well to solve them. Comment the answers and I'll be there to respond to them, whether they're right or they can use a little help. So first question says a sealed container has a pressure of 2.5 atmospheres at 20 degrees Celsius. What is the pressure at 100 degrees Celsius? And then the second question says a gas has a pressure of 4.0 atmospheres at 373 Kelvin. What is its pressure at 273 Kelvin. So I'd like you to try out your hands on them, get them solved, and comment the answers in the comment section where I'll be waiting to receive them. Up until next time when I come your way, it's bye for now. I hope you enjoyed every bit of today's lesson, and I hope it was able to educate you in one way or the other. Till I come your way next time, my name is David, and all we do on this space is to take the mystery out of chemistry so Chemi can make history. I'll see you in the next video.